All right, so just happy to just sort of jump right into it. I think for me, I've heard about Urbit. We received a grant. We work on Urbit stuff, but it is a fairly novel system. Obviously, its own languages, its own idioms, its own culture, its own history. And so I think I'll just sort of jump right into it. The thing that immediately stands out to me is when I run Urbit, it's called Urbit OS, but when I run it, I'm running it in Linux. So my very first basic question, as someone trying to understand or orient themselves to Urbit, is why the OS in the name, and is it an OS? Is it a VM? How would you, Joe, characterize it in those terms?
Yeah, that one's always fun. It's not a classic OS. It will maybe never be a classic OS in the sense of directly controlling hardware and orchestrating those resources and nothing else, is it has a higher level definition. When I first showed up, the website called it an operating function, which I actually really liked at the time and like to this day. But it doesn't answer any questions. It just raises more. But I do think OS is legitimate in the broader sense. I mean, the term is significantly diluted in the industry, but it's a complete specification of an environment, the whole life cycle of the environment itself and everything that's in the environment. So it's, legitimate if
And by environment, you mean like an environment that programs run it, right? Like
yes, a computational environment.
Yeah. So it's almost like a computing platform, and in the sense that it is like a computing platform, it also exposes identity services or authorization services. It exposes networking as well, right? So if I am a developer and I want to build an application that leverages Urbit, as I understand it, which is so very hard, I'm trying to figure this out. One of the benefits of me building something on Urbit is I do get this addressing the Urbit ID system and the ability to easily communicate. I don't need to open up a TCP socket. I don't need to necessarily even do marshalling or unmarshalling. It's very easy for me to leverage the existing, I guess, in Earth terms, I would say API of Urbit to address other ships. And so that's a clear benefit and part of why you're calling it an OS, right? Because if you look at something like Mac OS or iOS, there is no native notion of the other computer, right? I mean, I don't know I have to pick some idiomatic, there's all these different ways from a traditional OS that I could address another machine. And so, okay, that's super helpful. I think that's a great answer for that one. I guess then the next sort of question that I have is, again, sort of less philosophical and more technical, because you could answer this question very philosophically and we would just be here all day waxing philosophical. Like, what technical thing does Urbit provide? That could be a service, an interface, a function, whatever, that is hard for me to get like someplace else, like maybe just like the top three. Ted, do you want to?
Sure. Often I think of this, or I like to describe it in terms that I think people will be familiar with. So a lot of people have the Signal app on their phone. And the Signal app has a lot of very nice properties, right? It's end-to-end encrypted, it's open source, it's been audited, et cetera, right? So you can trust this thing in a lot of ways. But it's not extensible, right? So, and the people who run Signal have actually been trying to extend it with crypto payments, right? Mobile coin payments. Mm-hmm. But you can't do that in the US. Mm-hmm. And there are just a lot of limitations on that in general. And so, even the people behind it who are trying to extend it are running into problems extending it because the nature of that system is that it's not permissionlessly extensible, right? And so with Urbit, You can actually see the difference here where you have an app like Pals that each person installs on their own machine, and then that is permissionlessly extensible where the Groups app integrates with Talon's Groups app, interfaces with Pals. There are several other apps that also use Pals data and even use it for networking and whatnot to figure out who your contacts are, right? And that you traverse that social graph in different ways. And the difference there is that because Urbit is a personal server, right, like I can actually install something as a long-running service that is discoverable and addressable over the network. I can run that myself, and this is something that's almost impossible to do in any other way, right? And so there are a lot of details about how we get there and why we do things the way we do, but a lot of it is geared toward making it so that you can do that. And so, yeah, a lot of it has to do with exposing building blocks to application developers that include identity, exactly once message delivery, encryption, persistence, and peer-to-peer networking, right? So that, because otherwise, if you have to build that each time for each app, it's very difficult to do. And then instead of people running one Urbit server, which is hard enough, we want to make that easier, but that's much easier than running a whole fleet of Docker containers, each with their own app.
Agreed. And so I guess now I'm going to ask a slightly more challenging question. How do you folks see, I'm a JavaScript developer. Let's say I do write JavaScript under duress, but let's say I were...
As do we all.
Yeah, let's say I were an actual JavaScript developer and I wanted to take advantage of these functions and capabilities that Urbit has. How do you see, like I maybe we can touch on jets briefly, but maybe just sort of like organically through the conversation. How would you see, in like a short-term idealized view, how would you see a JavaScript developer taking something that maybe they were running on, I was running it on my Mac on Node, and now I want to run it in Urbit. Like, how would you see that happening?
Sure. So this is like a server-side process that you're running.
Yeah.
Yeah. Well, so there's a new Vane, V-A-N-E, kernel module in Urbit called Lick that Motful Winrux wrote. And we merged that not too long ago. And that allows Urbit to communicate with any other local Unix process. And it communicates using Urbit's data structures, nouns, that are serialized in Urbit's standard format over a Unix domain socket. And so what I would do is I would take that Node program, I would import the JavaScript noun library, which is actually quite good. It has an optimized deserialization function for nouns. At least it's somewhat optimized, right? I think it's pretty good, actually. And so I would import that and basically just add that as a new API connector on that existing server. And then you also have to write a corresponding application inside of Urbit to be the other end of that communication channel.
So, okay, so that's helpful. So what if I wanted to just run it, what if I didn't want to run another process outside of Urbit and I wanted to run that JavaScript code? So I'm sort of leading you because Ed gave me some hints by talking to him in the hallway. So how...
Maybe we can figure out where it's going, I don't know.
Yeah, so I'm curious because I think that this, what I'm trying to get at here is, I think that there's, for me, the philosophical alignment of Urbit is very straightforward. That's, which is important where we are in the world today. But then how that actually, I manage engineers. And so it's like, okay, guys, you looked at Hoon, you got very angry at me. You yelled, you complained, you didn't write any Hoon. And you don't like JavaScript either, but at least you type that when I ask you to. So we're making progress. How can we the thing I'm trying to achieve, so I guess maybe I should say a little bit about my sort of hypothetical thinking here and where I think Urbit has short-term utility, because I think there's like, again, this long-term vision, but you have to have sort of short-term steps to actually get to that long-term vision. And I think that where we are today with sort of censorship, centralized apps, Web 2, obviously I work in Ethereum, I think that we have a serious problem in Ethereum with app delivery. So those apps, unfortunately, have both fairly complex middlewares as well as modern, contemporary JavaScript-based front ends. And it seems as though Urbit actually solves a lot of the problems on the middleware side. And I can imagine, using Landscape and having used these apps on my phone that, talking to my ship from my phone, that the front end piece could easily be addressed. Like that's basically already done. I can create a desk and I can have my JavaScript in it. But there's a different type of integration that I think we would need in order to, I'm not quite sure what the right word is. We want something that adheres to the philosophy of Urbit and gets the benefits of the addressing and the networking, but is still more JavaScript. Like, quite frankly, again, I'm not a huge JavaScript fan, but it's where the world is. So like, I want to be able to write JavaScript and sort of run it on my ship so that I can get the benefits, so that I can have this, because what you described, I think, is also a useful model, a paradigm, where I have a JavaScript process and I want to leverage the benefits of Urbit. But even that is almost already too complex of a deployment, because like for me, I imagine I would probably need Docker in that deployment that you just
like what I was saying earlier.
Yeah.
Then you have a bunch of Docker containers next to Urbit.
And yeah, it helps. I've reduced some Docker containers. I've reduced, there's architectural benefits. But ideally, what I want to do is I want to be able to deploy JavaScript into my ship.
So you want to be able to run sort of pre-existing code inside of your Urbit. Is that sort of the general?
Yeah. That's and again in the theme of this talk. I mean, that's what I'm trying to understand. I'm trying to understand, as early contributors, core contributors to Urbit, how do you see that actually? Is that a valuable thing to do? Am I thinking about Urbit correctly? And then if that is a valuable thing to do, how do you see that actually occurring?
Yeah. So in full disclosure, you can't do this today.
Right.
So right now, I'm sorry, no, you're out of luck. But it's totally legitimate. The line that's popping into my head from, again, this original blog post that we cite chapter and verse in these conversations, is that the only way to run non-Martian software in a Martian computer is in a Martian emulator. So what does that mean? It means that you write a JavaScript interpreter in Hoon, which obviously is going to be not very fast. And then you jet it, which is where you said it'd come up naturally, with whatever you have. And you only have a small challenge, which is to make sure that they are exactly the same on all inputs. And if you do that, then it's totally legitimate. And so, this was suggested. I remember it might be in the Wayback Machine. You can find like a Google Summer of Code internship post for Urbit from like 2015 of like, hey, come integrate V8, we're gonna go for it. And I remember talking to people about this and saying, have you read like the JavaScript specs? Do you want to be doing this? So later I talked him down and said, maybe Lua will compromise and we'll find something with simpler semantics. And of course, the world has moved on in all sorts of ways. And there's a really, really nice target for almost everything but JavaScript at this point, and that's WebAssembly. Mm-hmm. And that's actually in progress. I don't have any of the details, but I know that if you come to demo day tomorrow, there are people in the hackathon actively working on a WebAssembly interpreter in Hoon. And as soon as you have that, I'm going to put a little asterisk here about floating point determinacy and then say, as soon as you have that, you can wire up an existing WASM runtime and Urbit is a deployment target for, I mean, anything that you can feed into LLVM.
Yeah, so that's great. So I think that's something to dive into, because we also have this sort of, well, in my mind, there's a little snake slowly approaching its own tail here, trying to slap it away. So if you have, and I think I'm going to see if I understand jets correctly. A jet is something where it's a process that runs, that the ship executes, where it's executing native code in some other language, and it somehow knows to take some set of Hoon and real time, just in time, convert that into a C binary, or calls out to something and does that. What is a?
That's not how I would describe it. So, the Urbit virtual machine runs Nock, right? So, Nock is all just a tree of numbers. It's all machine. It's very much like a machine code. People say assembly code. It's a machine code, really.
Yeah.
Hoon is the programming language that you type in, and then that's compiled to Nock. So it's statically typed, compiled language. But it gets compiled to Nock, and so then that Nock gets run. So whenever your Urbit receives a key press or a packet or anything like that, and it goes to run some code, it's running Nock. The Arvo kernel, like the Urbit kernel, that's a big blob of Nock. And so a jet is something that as the interpreter is running some Nock.
Okay, sorry.
It sees and then it sees an expression. Yeah, the Nock interpreter sees an expression, which is some tree. Mm-hmm. Like everything in Urbit is a tree, right? So it looks at the tree and it says, oh, I know what this tree is. This tree is the add function, or the decrement function, or the SHA-256 function. And so it says, okay, well, I could just run this tree naively. Mm-hmm. But actually, I know, the runtime, I have a function sitting here that is a SHA-256 implementation that I know is actually just faster than it would be to step through the Nock naively. And so instead of bothering to step through the Nock naively, I just don't, and instead I run this function that I have. And there's no programmatic or sort of formal guarantee that these are the same thing. Now, there's a little bit of work that's gone into this sort of the beginnings of trying to do a formal verification. You could do a proof and say these things are actually equivalent. Mm-hmm. We haven't done that in general. Mm-hmm. But I like to think of this also as like a built-in or an intrinsic, right? So in Haskell, you have something called a primop. Most languages, like Python, has built-ins.
Yeah.
Right. So Python, when you do A plus B, the Python interpreter, the bytecode interpreter, it also has some function there.
Yeah.
There's a spec for what that function is, and it just has to have an implementation that is correct, right? And it's like, okay, that's the same thing for a jet. So the reason that we have jets and not just built-ins is that we want this to be timeless, right? So the Nock spec doesn't depend on anything, right? It does, and it's very small. And then the set of jets that any interpreter has is up to that interpreter. So for example, Aries, the new Nock interpreter, its function calls are a lot faster. Its Nock function calls are way faster than Ver, the old interpreter. And so we have a lot of jets in Ver that do the same thing as the Nock, but because they're C function calls instead of Nock function calls, they go a lot faster. And in Aries, we don't need that because the function calls are fast enough. And so that interpreter just doesn't have those jets, right? So this is a way of separating the mechanism and the policy, right? Where the policy,
very good way of putting it. Yeah.
Yeah. So the policy is, here's the input, here's the output, right? There's this Nock specification that defines the transformation from the input to the output. And then the mechanism that gets you from the input to the output can be whatever you want. You just have to not mess it up.
And so are jets sort of in vain, because they're not in the spec, right? So this is what you just, basically, I'm just summarizing what you just said. The jets aren't in the spec, the jets are an implementation detail for Ver.
That's right.
And so, okay, so that's very helpful. So we can imagine something like an augmentation to Ver where when somehow you tag a tree that's being processed by the VM, that this is actually WASM, and it takes that whole expression, that whole WASM blob, it would be a byte array or whatever, and then pass that to its existing WASM interpreter. And I guess,
Exactly.
Are your trees composable? Do you have a tree of trees, do you have subtrees in your tree where this applies? So maybe I could have a tree that is at the root, like Hoon, Nock, and then I have a subtree that is WASM, and then it will be able to sort of execute that dynamically?
You could. There's an interesting thing here where you can kind of do whatever you want here, right? As a runtime, right? As long as you get the right answer in Nock, right? So as long as like that Nock input ends up getting the right Nock output, you can do this however you want. And jetting is not the only means that you have to do this, because there are also other hints. So Nock has 11 or 12 opcodes. The last opcode, Nock 11, it's right here, is a hint. And so what that does is it says, okay, we're going to run two Nock computations. The result of the whole expression is going to be the result of running the second one. We're also going to run the first computation and take that result and throw it away. So so the result of running the first computation can't affect the return value, right? It doesn't affect what comes out. But instead, because we have this special opcode there as a way of telling the interpreter something, and it's telling the interpreter a hint. So it says, okay, this can't affect what the result is, but it can affect how you get the result. And so we use this for debug printing, memoization hints, and jets. A jet is another kind of hint. But you can also have other kinds of hints.
Yeah.
And so if you wanted to have something that says, hey, maybe this is a partially jettable expression, for example. We don't have this construct.
Yeah.
But you could, where you say, okay, the rest of this computation is going to be, some of it you're going to want to run yourself, and some of it you're going to want to jet, and maybe you're going to want to jet it with your WASM interpreter, right? Maybe it's a mix of WASM and Nock, and you're going to want to thread the WASM through the Nock or something. Or maybe there's some optimizations you can do there, some kind of stream fusion or something, right? And so, yeah, you could theoretically do this. I don't know if I'd want to build it,
Yeah,
you could.
So I think that's an interesting question. I mean, thank you. That was a really helpful answer for me. Hopefully the audience, someone watching this at some point, will gain some insight from that. And it kind of actually going to maybe completely change topics here. So that sort of brings me to this next question of, so Joe, what is your development environment like when you are writing at these low-level things? So like, for example, we're just talking about var jets, and I could be taking a Nock tree, and I could be using a hint in Nock to move where that tree is actually getting executed. What sort of, are you using like Vim and like a command line compiler for this sort of work? How are you doing that work?
Yeah, that's basically ideal.
He claims he uses Vim. He actually just uses Sublime Text.
In practice, I created brain damage in myself because I switched from Vim to an experimental project called Cocoon, which is a really cool project. I'm not insulting it in the slightest. It's awesome, but its command syntax is like Pig Latin Vim, and so I broke my brain, and then I had to retreat. And then as far as command line invocations of the compiler, Urbit has a very unfortunate and fraught history of replacing its build system in misguided Sisyphean efforts. So unfortunately, I can't do that right now, but we'll get back. But yeah, so it's a very Var's actually a pretty pleasant working environment. Very unusual C idioms. Sort of like the whole thing is almost like a, not quite immutable, but expression-oriented DSL inside of C. It's been worked on for a very long time, so it has a very rich API. very unusual code style, not surprising. And so it takes people some time to ramp up to it. But having had to switch to other kinds of things, I think it's better than it gets credit for. It's quite pleasant to work in. I wanted to chime in on the jet question here real quick. I think Ted's answer is sort of the right top-down perspective. But as somebody who's come at it from the other side a fair amount, it's a useful like intuition pump to think of writing a jet as writing a plugin for an interpreter. It's very much the kind of attitude that you have and the kind of affordances that you want at the lowest layer. You want some of the context, the execution context of where you're at in the call. Maybe you want to peek at the stack, even if you really shouldn't. You want, to be parameterized over the kinds of allocations that you're going to do. And then you want things that are sort of, and the implementation, they never show up in the result, of course, but you want to be able to, say, partially accelerate some function. So you match the function and, you get invoked. But maybe some of the corner cases of the function are really, really unpleasant to write in C, and so you want to punt back to the interpreter if that happens and say, no, you. And so, yeah, just this thinking of it as, you build a generic interpreter, and instead of implementing all of its build-ins, instead you build a plugin system. And then, Ted's framing gives you the top-down, this is how, your plugins are declared and invoked and that sort of thing. And then, from inside them, those are the kind of affordances you want.
And what was the last one of those that you worked on, Joe? I don't know when the last time you worked on one would have been.
Oh, that's good.
I worked on the Min-Jet with Neil.
Nice.
Maybe a month or two ago. Neil?
Yeah, so I scratched an itch a couple months ago. I was talking to Edward, who's doing, the Aries project at the time. He was very deep in the code generation part of that. And so he's, basically writing compilation passes over an IR derived from Nock, recovering sort of the call graph, where Nock basically gives you a couple of different forms of eval, so you never know what your call target is going to look like, and his analysis is recovering the call target. And so he's doing lots of tree math. And of course, when I say tree math, I mean the binary addressing scheme. And so, every noun is a binary tree, and we use the standard, I believe technically it's the binary heap addressing scheme where, the root is 1, and the left child of that is 2, the right child is 3. In general, the left child of a node is 2n, and the right child is 2n plus 1. Yeah. And binary trees are so cool because, they map onto binary in very interesting and direct ways. So if you take one of those tree addresses and look at it as a bit string, the most significant bit tells you how many steps you're going to have to take to resolve the address, and then the bits tell you whether you go left or right.
Yeah.
And so we have, sort of a library of basic tree math, manipulation functions in Hoon, but Edward came up with some new patterns that he was experimenting with, and so he wrote those in Hoon, and he opened a PR with them, and so I thought, well, these will be really slow unless they're jetted, so I wrote kind of naive jets for them, and then I was looking at the existing ones that we had that we run all the time, and it's like, well, these are stupid, like one of them, so you'd say, like, for this address, am I gonna go left or right? Mm-hmm. And then after I go left or right, what's the rest of the address? Well, in binary terms, what you're doing when you do that, you're producing one bit, and then you're taking the most significant bit and shifting it right one bit. But it was implemented in terms of like produce the item that's this power of 2 and produce this power of 2 and then subtract them and then add them together. And it's like I can just do the bit math.
Yeah.
So that's actually the last jet I wrote, and it was just purely for the satisfaction of that kind of low level optimization. Because once I was in that corner, it was like this thing is doing maybe 10 arbitrary precision, uint allocations, and it's got to do ref counting operations, it's got to do all this other stuff. What I need is, an array of words and to move a bit, and I'm done.
So I think, well, again, for me, that's very helpful because it shows me, I think that explanation illustrated a number of things. One, it illustrated the sort of expressiveness and power of jets and how they interact with var. it elucidated for me where the state of the optimizations are. It also illustrated for me how you folks are making your optimization decisions, right? So vibes, apparently, which, I mean, is not the worst. There are worse strategies. I mean, you run into them. And so I think that this also sort of segues, you mentioned Aries, and then I think after we get into this, because this actually, and maybe we needed a little more bracketing around this, but I think this is helpful because when you're trying to, so we're trying to integrate with Urbit. So the first thing we did is we sort of fixed ETH Watcher to be independent of Infura, so that you can actually use our stack of software, which is a collection of Docker containers, to talk to dev P2P directly and get that information into the ship via the exact same method it used to talk to Infura in the past. And then as we were looking for, that's a very coarse integration, right? And as we're looking for tighter integrations, it is very, to be frank, slight critique, it is very difficult to read through your documentation and figure out how I would do that integration. And I think just listening to you and the expertise that you're expressing and also the style of the project actually really does help in figuring out how we would direct our engineers to actually work on Urbit. And I think part of that is also just to say that when we have interacted with the Urbit community, have been super friendly, super responsive, super helpful, again, in a way that other communities basically aren't for whatever one reason or another. So that's definitely part of that. And so you touched on Aries, and I think I have maybe I have more than a vague understanding of Aries, but I certainly don't have a robust, in-depth understanding of Aries. And I think, so again, my possibly incorrect summary is, right now you have a Nock interpreter written in C, var, and Aries is a means of, is a project to rewrite that interpreter leveraging something called LLVM, which is low-level virtual machine, for people who may not know what that is. And so LLVM is sort of sponsored by Apple, and it is basically a lot of languages get implemented in it. It's a back-end, front-end language processing sort of system. So at a high level, the net effect of it is, if once you are able to target LLVM, you don't need to rewrite all the optimizations that some guy wrote in 1973. You can just leverage LLVM for those optimizations. And so some of the stuff that Joe was just talking about, you kind of get for free, because you can actually get it into this IR that Edward is working on, and then the LLVM will figure out, oh, that was a silly way of doing this. Let me just optimize this in this other way. And so I think that's a super important project for Urbit. And how do you feel about, like, how do you feel, oh, it's hard to explain, but like, where do you think performance is today, and what do you think, and do you think that, I mean, so I'm just gonna make an assertion. I haven't even really evaluated it from like a benchmarking perspective. Everyone just tells me Urbit's really slow, and I just believe them. And so a project like Aries is helpful because, as I understand it, it does sort of change the jet story or the optimization story, and improves that optimization story significantly. And it also, again, maybe makes it easier for you to do this sort of WASM pipelining sort of stuff. But do you also see like something like Aries providing performance improvement that has some sort of qualitative difference that people would experience?
Yeah, so I'll try to take this from the top down. The thing on the T-shirt, and by the way, we did not coordinate.
Yeah.
Just to be clear.
Also,
mine is older.
Yeah.
This is Nock 5K. So
this is 4K.
any practical code written in either version of these, naively interpreted, is not even practical to run once, right? The only arithmetic operation is increment. To decrement a number, you count up to one less than it from 0. Addition is, you increment one in a loop while you're decrementing the other until it runs out. And then, every additional piece of arithmetic is implemented in terms of those basic operations. Every piece of, sort of binary data manipulation is implemented in terms of arithmetic. Very, very unusual, especially for something that calls itself a systems programming language. And so any sort of normal algorithm or whatever, you just very quickly get into a situation where you are incrementing atoms endlessly, and you're never going to stop. So some amount of jet propulsion is always necessary, which is why the only operation is increment. That's also an analytical snake eating its own tail, because you could say we're going to put more opcodes in it, and then some amount less jetting is needed, but it's just not an efficient approach to computation.
And since you're always going to need some jets,
you might as well need all.
You might as well just need all of them and say, okay, we're going to just have a very simple spec that you can build things out of, and then.
And so briefly, because even though we are probably going to go over, we also should be quasi-respectful of time. So, briefly, why is Nock written that way? Why is it so intentionally inefficient? What's the benefit? What do you get from that?
You get a lot of simplicity, basically, right? So, and then when you look at a Nock program, it's still, it is a machine code, but it has enough high-level constructs to do all the major pieces of control flow and other things that you do as a programmer, right? So Nock 6, the 6 opcode is if, right? If then else. Nock 7 is do this and then that, and you compose functions. Nock 8 is declare a variable. Nock 9 is call a function. Nock 10 is edit something, modify your state. Right? And then when you're writing Hoon is a very thin, very, very thin layer over Nock. So Hoon compiles to Nock that has no runtime system. Right? There's no little dongly bit of Nock that comes out in addition to what your code is. And so, when people think of Hoon as a tree-based Haskell, it doesn't look very good, right? Because as a statically typed functional language, it's pretty concrete, pretty low level. But if you look at Hoon as an assembly language for Nock,
yes,
where you get to stick names on different parts of the tree, and there's a little bit of type checking of is this tree the right shape, and you get to declare data structures where you say, yeah, here's something that's like a struct.
Yeah.
Right? Hoon data structures are very much like a struct. It's about which slot is which, and you name the slots. And when you think of it that way, then it's just a very nice, rich assembly language or C-like language. Yeah. And thinking of Hoon as a functional analog of C, I think, is the most correct. And you feel that after a while. The longer you write Hoon, you're like, man, I feel like I'm writing C.
In all the good ways. No surprise integer promotion rules.
No, right. We don't have those.
Strict aliasing.
We do have some problems with uninitialized variables sometimes. But yeah, so it's, but the reason that you want this, right? You want this machine code that you can actually, as a programmer, you actually know what all the opcodes are and what they do. And then the language that you write in, you know exactly what Nock is coming out of that. The only thing that's ambiguous to me about what my Nock will look like coming out of the Hoon compiler, the only thing I don't know is the actual tree slot numbers, which is what Hoon is supposed to abstract in the first place. So it does a very, very good job at that. And that whole system means that when I'm writing code, I know exactly what's going to be implemented, or what's going to be executed. Right? So it's that kind of very low-level control, and that's why we think of Hoon as a systems programming language, right? Because you do have this extreme low-level control over exactly what Nock is run, and each of those, and each Nock opcode is something that's very concrete. It's yeah, you're doing an if then else, or you're doing a function composition, right? There's nothing heady about any of it, and there's no place in any of that where like something can sneak in and you get a memory leak, or something can sneak in and you get an asynchronous call to a database.
So
right?
I think that elegance is very important, and that was an impassioned expression of I like this because it's elegant, but I guess what I'm trying to, which is a merit in and of itself, but I'm trying to understand, is there, is Nock easier to formally verify? Is Nock...
Well, so I'm not sure if he's in
a question
the
for Rick.
audience, but Zorp discovered that Nock was amenable to ZK proving much more directly and much more simply than any other kind of intermediate representation that they laid out, because they didn't, I mean, the thing that's so difficult about a ZK VM is establishing a model for the introduction and elimination of memory slots or something like that. And Nock completely, removes this problem, because you're talking about manipulations of a binary tree. They're all completely explicit.
Yeah, I would say that there are a lot of different kinds of elegance. Right?
Yeah.
And the kind that we're shooting for here, at this layer of the language, but also with Urbit itself, is that we're shooting for it to be elegant in terms of its mechanical simplicity, meaning like it's sort of each step is dumb.
Yeah.
There's nothing heady about any piece of it. There really shouldn't be. Every once in a while there is a piece of it that's heady, and we look at that and we're like, can we get rid of that? Can we make it dumber? And this is why we all really like Jonathan Blow. We really look up to him, the way he thinks about code, right? Where it's like, you want to have full control. You want to just build what you need. Don't overly abstract.
Yeah.
Right? Don't build like Rube Goldberg machines that you're never going to use, or when you do use them, you don't really know how they work, and so they sort of fail in ways that you're not expecting, or have performance problems that are difficult to characterize. And so, this is why like Nock is sort of maximally constrained, right? Like you only get pure functions. You only get this one data type, and it's really the only language that's used in production that I'm aware of that's pure functional, in the sense that all the language ever does is take an input and return an output, right? Most functional languages have some sort of escape hatch, so that they can do imperative input and output.
Yeah.
Right? And so for the way we do that, we keep the input and output separate. Okay, here's the input, it comes in as data. The output goes out as data. And there's nothing in that whole system, anywhere in Arvo, right? That whole tree, that's just one Nock blob. There is nothing in there that can do anything interesting or unique. Nothing in there is special, right? Like all of that is just a tree of numbers. None of those numbers are special. None of them are like a database handle where if you tweak it, then your process gets a deadlock, right? Like, there's no sort of there are no magical constructs that are outside of like this very limited set of building blocks that you're working with, and then that does translate to the programmer.
Yes.
And so like there is a bottom line win from this, which is that I can go and write an application. I write it as this function. I write it in Hoon, which has its problems, but it does have this nice feature of I know exactly what's going to happen once I know Hoon. And then that is just a function that runs, and it runs in this system that has very high level building blocks that are all standardized. So this is where it's like, the persistence comes in, right? I don't have to talk to an external database. I don't have to deal with fsync problems. And then I don't have to deal with some sort of login. I don't have to rebuild a login system, right? Because I just send to an identity, which is just a number, right? And like all of this system is designed so that each piece of it is really just a number, or just this sort of very concrete representation of the minimal version of whatever that thing needs to be.
And so do you think that the sort of philosophical power from what you just described, do you think that it's possible to sort of push that up into a JavaScript or a Python? So for example, let's say I am writing Python, but I'm targeting Urbit and again, this is actually where it does, we've come full circle. This is an operating system, right? Now, I'm writing a Python script but the operating system I'm targeting is not a POSIX compliant Unix operating system. I'm actually targeting the Urbit operating system.
Yeah.
And so I should actually experience the simplicity that you just described in my Python. I mean, that would be the theory. I mean, to me, that's
yes,
almost...
I would say yes, the answer is yes, I really do expect that to happen.
Yeah.
And that should happen with WASM, because there's a Python interpreter
Yeah.
in WASM, iodide,
Yeah.
and it has NumPy and SciPy and all this stuff.
And I think, because we have run over as predicted, I think that to me would be like a real milestone for the sort of the theory and practice combination of Urbit to say, here, we actually are running Python on Urbit. This is how you would write this application in Python targeting POSIX. Well, it's even, I actually do write a lot of Python. It's much worse than that. You say, I'm writing this Python for Mac OS, I'm writing this Python for Windows, I'm writing this Python. It's totally, the OS is not separated at all. So
it's not, yeah.
In some sense, you now have a fourth one. It says, okay, and I'm writing this Python for Urbit. And you would say, okay, I wrote it for Linux, which is the easiest one, and I still had all of this extra code. I had all this boilerplate, I had all these libraries, I had all this stuff. And then I wrote it for Urbit, and half of that, 90% of that stuff isn't really going to be there because the networking is already resolved, the identity is already resolved, all of these systems are already resolved. And I think that that's actually like a very concrete, empirical thing that you could do to demonstrate the power of the philosophy.
I think that's a great idea.
Yeah, just sort of as concluding.
If anybody wants to write that.
Yeah, concluding remark. We're over time, but if they said people could ask questions if they wanted. So, I mean, if anyone here has like one or two questions, I haven't looked at the audience at all, but yeah, there's a question. And I don't know if there's a mic, if I just threw these people under the bus here, if there's no mic coming.
Well, you could yell the question, you could repeat it.
Yeah. Okay.
For what it's worth, I do think that the phrasing you had there, that framing of you have some code that's running, on Linux, some code that's running on Windows, or you have some code that's running on Urbit. I think that's right, and that's why we think of it as an operating system, because it is this platform that you can target in any language that you're writing. And yeah, you can't use any language at the moment, except in certain ways. But yeah, that is how we think of it.
Yeah, absolutely.
All right, I think we're, okay, great. Well, as an Urbit maximalist, I one day hope that it is an actual operating system orchestrating physical hardware. Can you talk about what your thoughts are for things like Nock PU and what a jet might look like in instantiated physical hardware?
Sure. I like to talk about this, actually. So one problem that comes up in processors is the fact that they're so big. And so what you end up happening is they have different IPs. They'll reserve different sort of chunks of the space within the processor for different accelerators for different things. So you might actually have a SHA-256 circuit sitting there. Then you have big banks of floating point processors and arithmetic logic units for doing other stuff like that. You might have digital signal processing chips, neuromorphic chips these days, all kinds of stuff, right? And so they're just filling up the space in this processor with all these different things. And then there's an issue where when programmers and compiler writers go to write code to use the to use the processor, the sort of formal API for how you hook into the processor and get to do things is the instruction set architecture, the ISA, right? So that's like the machine code, x86 64, or ARM, right? But the thing is that that's just for dealing with the CPU, and it doesn't tell you how to talk to any of these accelerators, much less the GPU. Right, so what you have to do is then you have to learn all these different languages basically to speak to each different device that's in this chip. And this is becoming a big problem for hardware companies because they'll put all this different stuff in the chip and then programs don't use it because they don't know exactly which accelerators are there on which chip. Some of them have a SHA-256 accelerator, some of them don't. Right? And one nice thing about Nock with jets is that Nock is designed for something like this. Yeah, like sometimes you have a SHA-256 jet, and sometimes you don't. You write the same Hoon code no matter what. And there's a spec that says, yeah, okay, well, this thing's called SHA-256, so if it matches what the interpreter is expecting, then it can just use that. And the interpreter, broadly construed, is hardware and software, right? So right now we call Urbit an overlay OS. Going back to your original question, because you do for now have to run it on top of Linux or Mac OS. But it could kind of collapse down those layers. Now you're still going to need some piece of hardware eventually that runs Nock somehow. So if you have a Nock processor, then that's nice. You just run Nock on bare metal instead of having to translate Nock to machine code or interpret it with something that's written in the machine code for that existing processor. But whether or not we have a Nock PU that runs Nock natively, you could also have sort of an Urbit PU, Urbit processing unit, that takes all the pieces of its real estate within the chip and says that these are all circuits that implement various jets. So for any jet you have, just about, you could tape out a circuit, and you could have a parallel bank of those and do pipelining just like CPUs do for everything, right? And so then what you actually have is, each jet is a peephole optimization, right? It's an optimization for one very specific thing. And that's part of the reason we do it that way also, so that you don't have to have some more intelligent optimization in the interpreter. You can have a bunch of really dumb ones that says, is it this? Okay, then do it. But then, so there's a future here where a Nock processing unit, like ideally there is actually some way that it runs Nock that takes advantage of hardware, right? Where Motful Winrux's design, for example, is stackless. And so it doesn't even have a function call stack because it doesn't need one. It just allocates the nouns that are the intermediate products of any Nock computation, which is very elegant and very cool. So you could get speedups just there, and also speedups in the memory allocation, because if you have a specialized memory allocator in hardware that only allocates nouns, then you're going to be able to get some speedups. I'd put a bet on that, But then also, you get this what's called heterogeneous computing. Right, all these different accelerators, and as a user space programmer, you never have to think about that. You don't have to know which things are directly accelerated versus which ones have software jets or hardware jets. Right, you don't have to know that necessarily, and you can write the same code, and it'll get jetted maximally by whatever hardware and software, or hardware and firmware really loadout is on that particular chip. And so I think that this eventually leads toward potentially like high efficiency computing, right? Where ideally it goes fast, but also ideally it would use very low amounts of energy, because typically when you tape out any given function, routine, if you actually tape that out into hardware, it's usually much more energy efficient than running it in software, because software has all these extra layers, you have to move all the data around, and it's not sort of custom built. And that's increasingly important, right, for things like mobile devices and even just large-scale computation where the energy costs tend to get big. So I'm very excited about this. I think that oddly enough, it's like Nock seems to be at least somewhat promising as a solution for this sort of existing problem there.
Interesting. Well, thank you. We've gone well over, and we must wrap it up now. But this has been, I actually learned a lot. This is very helpful for me, and hopefully the audience learned something as well. Thank you.
Thank you.
All right, thanks a lot, gentlemen. Big round of applause.